In a previous video, we talked about SN1 and E1 reactions. In this video, I want to look at some examples of specific problems that are similar to what we might be asked on tests or quizzes. All right, so I think it's definitely important to be able to draw the mechanism for both SN1 and E1 reactions. And so our first example is to draw the mechanism for the SN1 reaction that would happen when this compound is heated in ethanol as the solvent. So the first step in both SN1 and E1 reactions is the loss of a leaving group, in this case, the bromide. So our first step, go ahead and put in my lone pairs. And so that's going to produce a bromide ion, or sometimes we might write like minus the bromide ion here on the arrow and not actually draw it as one of the products. Either way would be fine. All right, and then the second step is going to be the nucleophilic attack. And so that's where the ethanol is going to come into play. And of course, whenever we have a neutral solvent that's acting like the electrophile, we're going to end up with a positively charged ion, and that positive charge is going to be on this oxygen atom because it has 3 bonds in the one lone pair. And so we have the loss of the leaving group, and then we have the nucleophilic attack. And so those are sort of the main steps in the SN1 mechanism. But then whenever we have this positively charged ion produced, we're also going to have a proton transfer. So we'll have another solvent molecule come and deprotonate our substrate. All right, now we want to do the same thing for an E1 reaction. Now the first step is going to be the production of that carbocation, so the first step will be the same. And then rather than drawing the bromide as a product, I'm going to do what I said we could also do. So I'll do minus so we're losing that bromide ion. And again, we produce that carbocation. And then the next step for the E1 reaction is the elimination of one of the beta hydrogens. And so I didn't draw any of the hydrogens in here. I think we probably want to go ahead and draw that so that we can see what's going on in the mechanism. So I'll go ahead and put the hydrogens in here. And so now we'll have the proton transfer. The carbon-hydrogen bond will become the double bond here. And so that will be our final product from the E1 reaction. All right, this question is about solvent effects. And so we want to know whether this process, and so this would be the first step in either an SN1 or an E1 reaction. And for both SN1 and E1, this would be the rate determining step. And we want to know, is this faster if we used water or diethyl ether as the solvent? And so hopefully you know what water looks like, but I've also drawn diethyl ether down here. And so what this question is getting at is that both SN1 and E1 reactions are faster in polar protic solvents because the protic solvent can hydrogen bond, right? And that greatly stabilizes both the carbocation intermediate and the leaving group. And so water is a polar protic solvent, diethyl ether is a polar non-protic solvent, and so we would expect the reaction to be faster when water is the solvent. All right, in the next couple questions, we're going to look at what the effect of the substrate is on the rate of the reaction. And so I want to know which one of these compounds would undergo solvolysis more rapidly in water, right? So which one is going to form the carbocation faster? And so these are constitutional isomers of one another. And in both cases, bromine is a leaving group, right? They're both taking place in water. So the difference between these two is going to be what is the stability of the carbocation that's formed. In the case of the first molecule, will form that carbocation, whereas in the case of the second molecule, will form that carbocation. And so because the tertiary carbocation is more stable than the secondary carbocation, we would expect that this compound to undergo solvolysis faster. Okay, here's another example. And so again, the solvent's water in both cases. Bromine is the leaving group in both cases. So the difference, the only difference again, I think, is going to be in the carbocations that we produce. And so in both cases, we produce secondary carbocations, but the one on the left is going to be more stable because I have a carbocation allylic to a pi bond, and so right, we're going to get resonance stabilization. And I could draw another resonance structure where I move this pi bond over. And so because this compound's carbocation is stabilized by resonance, it's going to react faster. Okay, another similar example. So again, the solvent is the same. And I think the carbocations that we produce are going to be the same, right? Whether I pull off that chlorine or pull off that iodine, right? We're going to get this tertiary carbocation, and it's stabilized by resonance. But the carbocation is the same. And so the difference on this problem is the leaving group. And so we want to know whether the chloride ion or the iodide ion is more stable. And so if you remember, when we talk about the stability of bases, right, we think about ARIO, right? And so in this case, the atoms are different, right? And the larger atoms are better at stabilizing the negative charge. And so the iodide is going to be more stable than the chloride ion. Or another way to think about it is the iodide is a weaker base, and so it's more stable. And so that means that this compound is going to react faster. Okay, in the last couple examples, we are going to predict all of the possible products from the solvolysis reaction. And so we need to predict both the products of the SN1 process and an E1 process. So for this compound, let's think about substitution first. In general, unless the alpha carbon is chiral, there's only going to be one substitution product. And so in this case, we're going to replace the bromine with the oxygen attached to a methyl group. And so our substitution product will be that. For the elimination product, there are generally more potential options. And so we need to identify what our beta carbons are, right? And so I've got a CH3 here, a CH3 here, and a CH2 here. Now these two CH3s are chemically equivalent, so whether the elimination occurs with either one of these CH3s, it's going to give rise to the same product. But then I also have the elimination that can occur from this carbon. And so why don't we draw the ones by pulling off a hydrogen from the methyl group first. And so that would be one of the E1 products. Now, I've got two hydrogens coming off here, and so I don't have to worry about E and Z or cis and trans isomers because this is not stereoisomeric. And then the other elimination product would be eliminating from one of those hydrogens. And so that would look like this. So this would be our SN1 product, and then these would be our two E1 products. Now, the problem doesn't ask us to do this, but among the E1 products, oftentimes we're asked which one is going to be the major product and which one is going to be the minor product, because this one is tri-substituted and this one is only di-substituted. We'd expect that this would be the major product, the major elimination product, and this would be the minor elimination product. Okay, here's another example. So we need to predict all of the products. So if we do substitution first, again, if the alpha carbon isn't chiral, then I typically only have one substitution product. In this case, we're going to replace the iodine as our leaving group, and we're going to get an OH in its place. So our SN1 product would be that. And so then if we consider the elimination, we need to look for our beta hydrogens, right? Well, I've got a beta carbon here and here, but neither one of those have any hydrogens. So elimination isn't going to be possible from either one of these centers. And so the only place I have beta hydrogens is from this methyl group. And so in this case, we're only going to get one elimination product. And then again, because these tert-butyl groups are chemically equivalent, as are the hydrogens coming off here, it's non-stereoisomeric, and so we don't have to worry about any cis and trans or E and Z isomers. And so in this case, we'd have two products, one SN1 product and one E1 product. Okay, one last example, and so same thing. We want to draw all the expected products from the following solvolysis reaction. So if I'm going to look at substitution on this slide, and then, because I think I'm going to run out of room, we'll do elimination on the next slide. Now, in the previous examples, the alpha carbon was not chiral, and so there was only one substitution product possible. But now, because I have a chiral center, we'll have two substitution products. We'll have one that retains the configuration and one where the configuration is inverted. And so our two substitution products so we'll have one where we don't have an inversion of configuration. So, right, the oxygen and the ethyl are in the same position as the chlorine, but then we'll have another one where we invert And now this methyl group is going to be in the back. All right, so in this case, we have two SN1 products, one where the configuration was inverted, one where the configuration was retained, and then on the next slide, let's consider the possible elimination product. All right, so we need to look for our beta hydrogens. So no hydrogens here, so I think our two possibilities are here and here. So if we consider this one first, that product is going to look like this. And then we can also have elimination from here. All right, now, our first elimination product, we've got two hydrogens coming off here, so it's not stereoisomeric. But in this one, I've got a hydrogen and an ethyl, and I have a phenyl and a methyl. And so this one is going to have, it's not going to have cis and trans isomers, but it is going to have E and Z isomers. And so the one that I've drawn, I think the high priority groups are on opposite sides. And so this is the E isomer, but we're also going to have the Z isomer. So we can also have and now I'll swap. So I've still got the double bond here, but now I'm going to put the hydrogen down and the ethyl up. And so we said this was the E, this was the Z. So in this case, there are three elimination products. And just when we had multiple elimination products in a previous example, I think it's helpful to rank these in terms of which one is going to be the major and the minor products. So I think when I look at these, they're both tri-substituted, whereas this one's only di-substituted. So this is going to be the most minor. And then when I compare these two, to know which one is going to be the major and the minor between these two, I want to look at steric hindrance. And so my two biggest groups, I've got the ethyl on this side and the phenyl on this side, are on opposite sides. Whereas in this case, the ethyl and the phenyl, the two biggest groups, are on the same sides. And so this compound is going to have greater steric hindrance. And so the first one will be the major product, right? This one will have the second most and will have the least of this one.